Okay, welcome back everyone. In this video, we're going to start our discussion of electric flux, which is the topic of chapter 22. Now, last time we were looking at the motion of charged particles in electric fields, and we looked at what happened when a particle was just sitting at rest to begin with, and we found that it accelerated with a constant acceleration. And I meant to do this problem as well, so we'll just do this as review right now. But we want to find the velocity and position of this electron 3 nanoseconds after it enters the field. So if you think about it, this is kind of like a projectile problem, but because it's an electron, it will go the opposite direction against the electric field. So when the particle is right here, for example, it will feel a force to the left. So that means that, well, it actually will never be right there because it's going to follow a curved path like this. So there's the force, but there's the parabolic path. If you think about it, if this was the gravitational field pointing down towards the surface of the Earth, and you had a baseball that you threw, it would curve this way because the force of gravity would be pointing downwards. This is the same concept, that we have a constant y velocity but a changing x velocity because of the electric field. So then the way that we would set this up excuse me, is just to say that ax would be the same as in the previous slide, and we found that that was QE over m, which was 5.63 times 10 to the 13th meters per second squared in the negative I hat direction. Now we do have initial velocities. We have Vx initial is 0 and Vy initial is going to be 20,000. And Vx is going to change because we'll have Vx final equal to Vx initial plus Ax times t, but Vy is not going to change. So these are the velocities, and actually the velocity of this particle will be the same as what we had last time, that we just take the acceleration and multiply by 3 nanoseconds to get, after 3 nanoseconds, we're going to get that Vx will be the same, so 20,000, and Vy will be 169,000 in the negative I hat direction, and that would be positive j hat. Okay, so if we want to find the position, then we can just calculate x and y, and so our calculation for x final is the exact same as before. Okay, that x final will be basically 1/2 ax t squared, and that will be negative I hat, and then y final is just going to be Vy initial times t, and that'll be in the positive j hat. So if you want to put some numbers in, so x final would be about 2.53 times 10 to the minus 4th meters I hat. And y final would just be 20,000 times 3 nanoseconds, so it'd be plus 6 times 10 to the minus 5th meters j hat. And then you can combine vectors in order to find the total position. And we won't do that right now. But let's move on, because the topic of this video is flux. So flux just means flow. So if you think about a random vector field V shown below, then you think about 3 wire loops that are in this vector field. Here's one which is sort of edge on, okay? So it's like a piece of paper that we're holding up. Here's one which is sort of facing us, and here's one which is kind of at an angle. Which one of these has the maximum flux or flow of the field lines going through it? And it turns out that it's the first one. Now you can't see it, but this one right here is the maximum flux. This one has no flux, and this one here is sort of intermediate. Now how do we know that the middle one has zero flux going through it? So if you think about a sheet of paper and you turn it on its side, then none of these vector field lines are actually going through the piece of paper, as in the first or third diagrams. So this is the concept of flux. And in order to change flux, we have to do a couple things. We can increase or decrease the magnitude of the field, and that's important to make note of. We can increase or decrease the area of the loop, and we call that A. This would be the magnitude of V. Okay, now the area of the loop is actually going to be a vector, and we'll talk about that in a second. And then we can change the angle of the loop. And you can see right here that we have an angle of the loop with respect to the vertical. And those all have the effect of changing the flux. Okay, so let's talk about the area vector. This is a vector that's perpendicular to a surface with a magnitude equal to the scalar area of the surface. So we're going to introduce a new unit vector, and you might have seen this, but we're going to introduce n hat. Now n hat can be in any direction we want, but this is called the unit normal vector. So you may or may not have seen this notation before. And that means that the area vector A is defined as the magnitude of A times n hat. Sometimes we just write the magnitude of A in order to avoid confusion as just A. So this is a definition of the area vector. It is a vector that points in the n hat direction. So this would be n hat, this would be n hat, and this would be n hat. And those are all different numbers. Okay? In the first example, n hat here could be I hat. Or maybe it's a j hat if we have a three-dimensional system like this. That's going to be I, j, and k. So maybe this one is actually just j hat. This one might be I hat, and this one right here might be a combination of j hat plus k hat, and we would have to divide that by root 2 in order to make that have a magnitude of 1. So don't worry too much about that. The point is that an area now has a vector that signifies which way it's pointing. And what we want to do is think about the angle between the field vector and the area vector. And if we look at this, which angle do we have maximum flux for? So we have maximum flux when the angle is actually 0 degrees. If you look at this first case right here, the field is going to the right, that's V, and the area vector also points to the right. Both of them are in the j hat direction. So that's where we have the maximum flux. And actually we have 0 flux when the angle is 90 degrees. So think back, if you took mechanics, think back, okay? The flux is proportional to the field vector magnitude, it's magnitude of V, the area vector magnitude, area of A, and the cosine of the angle theta between them. What does that remind you of? What does that sound like? Well, it turns out that is the dot product. So flux is the dot product of two vectors, v dot a. Now they're in bold type on my screen here, but just to be clear, v and a are both vectors, and flux is a scalar. Now a scalar can be positive or negative, but it comes from the dot product of two vectors. Okay, so now if we replace a random field with an electric field, we get a similar equation for flux. We get that electric flux is equal to E dot A. So that's just our definition. And the units for this, because area is meters squared, whoops, got ahead of ourselves there. The units are newtons meter squared per coulomb. So A is meter squared, E is newtons per coulomb. Okay, now when we're thinking about a closed shape, we can have different area vectors. So this rectangular prism has 6 surfaces, and each one has an area vector that points outward from the center of the prism and is normal to the surface. So here are some of our area vectors, and before we picked I, J, K. Okay, so this one could be A, J hat, this could be A, I hat, and this could be A, K hat, but they're all equal to A, N hat. It's just that N is in different directions. Okay, here's another example. If we have a cylinder, then on the top and the bottom, it's easy. It's just A is equal to A, I hat, J hat, or K hat. We'll call it N hat, okay? But now on the side, we want to break it up into little pieces because the normal is going to change on the surface of the cylinder. And as a matter of fact, right here, it might be pointing kind of this way. And over here, it might be pointing kind of that way. So when we have a more complicated surface, we break it up into little pieces dA. So how do you calculate flux over a closed surface in a vector field? Well, at every point on the surface, you take the dot product with the vector field to get the flux. So you have to do the vector field dot dA for every piece. Then you have to add all of those dot products up to get the flux for the entire surface. So this, if you think about it, is d flux. Okay, so there's kind of interesting things that happen. If there's a source of the vector field, then the flux over the surface is positive. If there's a sink of the vector field, then the flux is negative. Now to connect this to charges, well, first of all, if there's neither a source nor a sink, then the flux is 0. But to connect this with an electric field, the source is where the field starts and the sink is where the field terminates. So if you think about a positive charge, that is a source of electric field lines because field lines come out of a positive charge. And a negative charge is a sink because field lines go into a negative charge. Therefore, if a closed shape encloses a positive charge, the flux is positive. If it encloses a negative charge, the flux is negative. And if it encloses 0 charge, the flux is 0. Or if the net charge is 0. So for example, you could have a positive and a negative. And if they are inside of a closed shape, then the flux is 0. Okay, so mathematically, for a general vector, we say that flux is the surface integral of v dot dA. So what we're doing is we're calculating the flux at all points on the surface, and we're adding them up. So for an electric field, the electric flux just looks like this. It's the surface integral of E dot dA. Now sometimes you'll see a surface integral with 2 integral symbols, sometimes you'll see it with 1, but the meaning is clear because we're integrating with respect to dA. Now, most of the time, we're not going to be doing complicated surface integrals in this class, but you need to understand the concept in order to see what happens next with Gauss's law. So, speaking of that, the closed shape that we integrate the flux over is called a Gaussian surface. And we'll do one quick example and then move on for next time. Okay, so calculate the electric flux through a spherical surface of radius 2.0 meters containing a point charge of 3 millicoulombs at its center. So our equation is that electric flux is the surface integral of E dot dA. And that looks imposing to do a surface integral, but what we can realize is that if this is a charge of plus 3 millicoulombs and we have a surface with a radius of 2 meters, well, everywhere on the surface, E is going to be pointing out, and so is dA. Now I'm not going to draw a whole ton of them, but like here, for example, we have E pointing out and dA also pointing out. Because of this, a couple of things happen. First of all, the dot product goes away. Because E is parallel to dA, the dot product is simply times the cosine of 0, which is 1. So it's the integral of just E dA. Okay, and this is because E is parallel to dA. Now we're back to magnitudes. We don't have vectors. Okay? The next step is to recognize that at every point on the surface, E has a constant magnitude at R equals 2.0. Why? Because this is a test charge, this is a point charge, so its electric field is simply kq over r squared. Nothing changes when you move around the surface because r stays constant. This means that if E is a constant, it can get pulled out of the integral to turn into E integral dA. Okay? Now, we're going to write this slightly differently, where instead of K, let's write the electric field as Q over 4 pi epsilon naught r squared, because that's what K is 1 over 4 pi epsilon naught. Okay? So we put that here, Q over 4 pi epsilon naught r squared. And now, think about this. What is the surface integral of dA? Well, we have a spherical surface. That is just simply the area of the sphere, which is simply 4 pi r squared. That's what the integral turns into. And most of the time when we do flux, we're going to have a nice amount of cancellation because of symmetry. So the 4 pi r squared cancels out, and we get that the flux for this shape is equal to the charge Q over epsilon naught. Now the numbers aren't even important. The most important thing looking at this is that there's no dependence on anything aside from a constant and this Q, which is the charge enclosed by the Gaussian surface. And this is going to lead us into Gauss's law next time, but we're going to stop for now. See you then.